So, we will do 2 sessions today before we wind up. So, this current session is the x86 instruction set architecture session. So, as I told, the instruction set architecture is the interface between the hardware and the compiler, right. So, the compiler, in the last session we saw there was a C code and there was an equivalent machine language realization of the C code. Who does this translation? The compiler. So, the compiler needs to have a knowledge about the instruction set architecture for it to translate from a C code to the corresponding instructions. Now, what we will be dealing now is the x86 instruction set architecture. What are all the instructions available in the x86 Intel hardware, and how do you use this instruction set architecture for this, right. So, let me give you some philosophy about instruction set architecture, right. There are 2 philosophies about instruction set. One is what we call as the complex instruction set computer, and another is called the reduced instruction set computer, CISC versus RISC, right. The x86 that we are going to study now is a complex instruction set computer. The ARM which we will be studying towards the end of the course is also a reduced instruction set computer. In a reduced instruction set computer, I will be giving some simple instructions, not really simple, but limited amount of instruction, and then the compiler has to use these instructions to realize certain functionalities. In the CISC, I will give you a lot of instructions. CISC is a compiler's heaven, but the architecture's hell, okay. Because compiler, whatever it wants, it has an instruction which is available, so it can quickly translate it, but the architecture will struggle to basically execute them, because there are so many instructions which the architecture has to understand and execute. While RISC is architecture's heaven, I have only a simple set of instruction, compiler has to break its head, okay. Computer science is also communist science. What is the rationale of communism? You lose something, you get something, you get something, you lose something. That is a law of averages is very good, right. Nature, for example, is very communist. You start exploiting her, she gives back, right. So, computer science is also like nature, right. So, you lose something, you gain something, you gain something, you lose something. So, in CISC, what you gain? Compiler will be happy, but the architecture will be breaking its head. In the RISC, architecture will be happy, compiler will be breaking its head, okay. Now, there are, if you take courses in advanced architecture, there is something called executing a CISC instruction in a RISC framework. There is something called code morphing, right. We will not go through this in this course, it is an architecture course, okay. But we need to have an understanding between CISC and RISC, though it doesn't have any impact on security, but a good understanding of it is much important from this point of view, okay. Now, an instruction set is called an orthogonal instruction set, right, if a particular instruction, every instruction will have an operand and then which is called an opcode and an operand. Say add, we said, right, compare EAX comma EBX, compare is an opcode, EAX and EBX are operand. We had move EAX comma 0, right. So, move is an operation or an opcode, EAX and 0 are operand. Now, there are 2 different types of operands. One is a register operand which is stored in the register, like compare EAX comma EBX, both EAX and EBX are register operands. But if you say move EAX comma 0, EAX is a register operand, 0 is a memory operand. An orthogonal instruction set is one in which independent of the operation, I can go and access any operand in any form. So, there is no connection between the operands and the opcode, right. I can't say for this particular opcode you should use only this type of operands, this opcode, right. I cannot use some type of operand. or when I use this opcode, some operands are already implied by it. Right? There are instructions, we will see as we proceed, if possible we will see that there are instructions where some of the operands are already implied. Right? For example, the string instructions in the x86 architecture, move string, right? Move string is just a 1 byte instruction or 1 or 2 bytes instruction, but then what will it move? It will move a bunch of bytes from one location to another. So the source location, the number of bytes will be in a register called ECX, right, and where should I move will be in some EIX, EDX and some things. So there are a lot of things. So at least 4 to 5 registers have to be set before I execute this move set. So this instruction depends upon the values of those registers which are implicit. Right. Before I execute move SB, I have to go and set many registers and then execute this. Right. That type of an architecture, instruction set architecture is not orthogonal. An orthogonal instruction set is one where my opcode I have to add, and wherever that location I should be in a position to use it. So the opcode is independent of the operand. You got this? So what happens here? When I want to decode, it becomes very easy for me to decode if I have an orthogonal instruction set. Otherwise, which register should I go and fetch, etc., if it depends, then I have to finish off the opcode, and after seeing what the opcode is, then I have to start fetching what the registers are, right. So that means your decoding becomes much more complex in a non-orthogonal instruction set architecture. Okay. So all the RISC architectures that we see, especially ARM, right, they are all orthogonal instruction set architecture to a large extent. That is, your opcode and the operand can be handled concurrently. Where the operand lies is independent of where the opcode, is independent of the opcode, right. Now please understand that we have talked about that communist stuff, right, meaning the law of averages. So now let us look at this. When I look at programming language, the execution of the programming language, there are 2 translations involved. The first translation is your C program gets translated to machine language using your compiler. That is an explicit translation, in the sense you see the compiled code. The next translation is your compiled code is actually interpreted by your hardware and executed. So there is one implicit translation happening internally. That is what people forget, or books fail to explain. Right? There is another translation that is happening where the hardware accepts your instruction, decodes it and then executes it. Right? Right? So the first one is called compilation. What is compilation? Take a code, completely translate it into hardware. What is interpretation? Take instruction by instruction, execute it, then take the next instruction, again execute it one by one. Right? Take an instruction, decode it, execute it, next take another instruction, decode and execute. So in the first level translation is a compilation for us. The second level translation, where each assembly instruction is taken by the hardware, understand what it is trying to do and then executing, which the hardware does, that is an interpretation. So that is one common question you will be asked, what is the difference between compilation and interpretation? This is the difference between compilation and interpretation. Compilation is done by the compiler, interpretation is done by the instruction decoder in your hardware. Please understand that there are 2 important levels of translation that happens, right. One is a programming language, when I talk of a programming language to execution, so there is a compilation that is done by the compiler, which is one translation. There is an interpretation that is done by the interpreter, which is there is a translation done by the instruction decoder, which is interpretation. Okay, right. Now there is memory. Accessing memory is very time consuming, right. So what I do, from the memory I take data and put internally, do all calculation, and once in a while go and update the memory. This is how the code gets compiled. Every time I do not go to the memory, from memory I take the data and put it inside the processor in some locations and use it, and finally I write it back to the memory. Those locations are called as general purpose registers. Okay. Now from now on I will be actually talking about some of the complexities in Intel, right, and let us try and appreciate. Right. Now Intel originally was a 8-bit architecture, then it became a 16-bit architecture, then it has become a 32-bit, now 64-bit. In the 8-bit architecture there were 8 registers. Registers are scratchpad memory. I bring some from the memory I bring some value and I store it in the register. As you see in the slide, there were 8 general purpose registers in the 8-bit architecture, and they were AL, BL, CL, DL, AH, BH, CH, DH. There were 8 8-bit registers. Okay. Now as it became a 16-bit architecture, what they did, they merged AL and AH to form AX. Today when I say AX is a 16-bit register. If I say AL, it is the first 8 bits of that 16-bit register. If I say AH, it is the next 8 bit of that 16-bit register. Why I am doing this? Because I want to maintain legacy across code. Still my original 8085 code should run in today's context, and that is the reason why I have this sharing of registers. Similarly, BHBL, CHCL and DXDL becomes BX, CX, DX. And then the 16-bit introduced 4 more registers, namely SI, DI, BP and SP, where SP actually stands for the stack pointer. Now the 16-bit got extended to 32-bit, so they added 16 more bits as you see on the left hand side. Now and named these new registers as EAX, extended AX, extended BX, extended CX, DX, SI, DI, BP, SP. So the extended AX, extended whatever EAX has the lowest, there are 4 bytes in it. The lowest of the byte is AL, the second lowest is the AH, the second and the first lowest is form what do you call as AX, right, of 16-bit, and then the entire thing becomes EX. Why I need this type of a general purpose register organization is specifically to maintain my legacy. What it means to maintain the legacy? It means to maintain the legacy from this point that whatever code I have written should still execute, and how much ever memory I have allocated at that point of time should be the one that is allocated. So these are some of the reasons of why an Intel general purpose register, this is called a register file because it has file a collection of registers. Why should it be complex and what is the complexity is what you see in this file. In addition to this, there are 6 general purpose registers, namely CS, DS, ES, FS, GS, SS, as you see on the leftmost side of this slide, which are all different segment registers we use. The segment register is one which stores the base of the segment as I explained earlier, and you have these 6 segment registers here. Now this particular 32-bit architecture has now become 64-bit and above. So RAX, RBX, RCX, RDX, RSA, RSP, RDI, RBP, these are all the 64-bit general purpose registers sharing space with its corresponding 32-bit register. Okay. So RAX is 64-bit, in which the first 32 bits is called EAX, in which the first 16-bit is called AX, in which the first 8-bit is called AH and the next 8-bit is called AL. Similarly, I can go for EBS, ECX. In ESI, RSI is a 64-bit version of ESI in which the first 100 bits sorry, the last 32 bits will be ESI and the remaining first 32 bit will be the extension of that. So in addition, there were some more general purpose registers that were added, which was R8D to R15D, which was 32-bit counter part, and R8W to R15W, which is the 16-bit counterpart. So, in addition to these 8 general purpose registers, there were 8 more 32-bit registers and 16 more registers, general purpose registers are added, right. So, the 32-bit are R8D to R15D and 16-bit are R8W to R15W. Then you have floating point registers, 8 of them, ST0 to ST7. Then you have multimedia registers, which are 64-bit. As I told you, the multimedia operations involve bitwise AND. I can do 64-bit ANDs in one shot, and that improves my graphic speed, etc. And that is why it is called multimedia instructions. And then packed integer and floating point arithmetic, there are 128-bit registers, which are named XMM0 to XMM7, and these are the 128-bit registers. Okay. Then there are 6 segment registers, namely CS, DS, SS, ES, FS, GS. The CS is for the code segment, DS is for the data segment, SS is for the stack segment, and then there are 3 additional segment registers, ES, FS, GS, which are the extra segment registers. Okay. Now, I will just give you this code. Now, in this setup, there are 4 segments, namely DS, one pointed to by DS, one pointed to by SS, and one pointed to by ES. So, there are 4 segments in which 3 are data segments. One is DS, another is ES, another is SS. SS is essentially a stack segment, which is a data segment, because data is stored in the stack. And there is another segment called CS, which is the code segment, which points. So, as you see, DS is pointing to 500, SS is pointing to 2500, ES is pointing to 3500, while your CS, the code segment, is pointing to 1500. Okay. Now, when I say move 10 comma EAX, what will happen? The value stored, where is DS stored? DS is stored in 500, DS stores 500. So, the value in 510, the value of EAX will be moved to the 510 memory address. And the opcode which of compiling move 10 comma EAX is 0x89, 0x05, 00510, right. This is hexadecimal, 89, 5, 5, 10. This is the opcode for, if I compile move 10 EAX, this is the opcode I get, this is the which I give to the architecture for executing. Now, this is every time DS is added, but now I have 2 more segments, right, SS and ES. I have 2 more segments, namely SS and ES. What is SS, what is ES? They are also data segment. How will I access data in that SS and ES? If I say move 10 comma EAX, it is only using DS, right, correct. So, the instruction say move ES colon 10 comma EAX, if I put that ES, then it will now access from what, where is ES pointing to? 3500, it will now start accessing from 3510. So, I can access from any of the data segments, not necessarily only DS, but ES, SS, FS, GS. So, I can, by just adjusting that, instead of DS, if I put default it is DS, but if I put ES colon, then it comes from ES. So, when I go and compile this, the opcode is again 0x89, 0x05, 0510, okay. This is the same opcode, but then in addition I have one prefix which is called 0x26, which tells for this instruction it is a move instruction, okay. This is a move instruction, but move it from what? ES, use the segment register ES and not DS. That 0x26 in front of 0x89, 0x05, 0510 basically tells me what? Move it from 0x26. Move it from ES, use the ES as the segment register rather than SS or DS. So, this is the basic thing. So, with this as a background, let us quickly go through this slide. So, I have multiple segments, I need multiple segments for some reason. I will ask at the end of this slide, I will ask you why do we need multiple segments. Let us see how many of you answer that. The segment register can change its value to point to different segments at different times. So, the x86 architecture provides additional segment registers to access multiple data segments at the same time like DS, ES, FS and GS. x86 supports a separate stack segment register and a code segment CS in addition to this. So, there are 6 segment registers. By default, a segment register is fixed for every instruction for all the memory access performed by it. For example, all data accessed by move instruction takes DS as the default segment register. Now, if I want to change that DS to ES, then I put something called a segment override prefix, right, and if I use that segment override prefix, then your DS becomes whatever other segment you want. And so, this 0x2 is 6 is a segment override prefix. Why it is called prefix? Because it is happening before the instruction. And why it is segment override? Because it changes the segment which you want to add, right. So, by using segmentation, I have multiple segments and I can access all these segments as a part of the code. Why do I need multiple segments? Why do I need multiple data segments? I need multiple segments, one for code, one for data, one for stack. Why do I need multiple data segments? Can you just go back to your C programming fundamentals and tell me why do I need no, why do I need multiple data segments?
To perform the same operations or different data.
No, I can put it in the same thing, and one data segment I can put all the data and access it. No, why should I need multiple? Can you give me one reason? Huh? Contiguous space will not be available. Why contiguous space will not be available? See, everything is in the stack, all the local variables are in the stack. So, everything is with respect to the stack segment itself, I can access it, right.
If we need to access multiple data with the same instruction.
Multiple data with the same instruction, but they will all be within one data segment, right. Why do I need multiple data segments? Can you go to some programming constructs and give me an answer? Programming constructs with
separate the input data from the processed output.
no, there is nothing like separation. When I give a data to the process, it becomes process data, right. So there is no,
Inputs may be used by some other program.
then it is for that data segment. Why in a particular, as a single program, why should I use 2 data segments? One thing is clear, that we need contiguous space. Yes, I agree that we need contiguous space. Other than that, so because of that what? Please note that we have a call called malloc. What does malloc do? It creates a new set of addresses, right. Now, when I do a malloc, I have already a data segment given to me. When I compile, I know these are all the data I need. So, there is a data segment given in which all data I could realize or I could interpret at the time of compilation. So, I say I have 100 integers in this program, so 400 bytes are given to me. But then there is something like malloc which I do not know, correct. So, when I execute a malloc, what happens? Another set of data I need to allocate, say another 1000 bytes of data, right, that I will know only dynamically. Now that for that 1000 bytes I cannot have it contiguous, correct, because all data should be contiguous, the segment should be contiguous memory locations. I may not have contiguous memory location to store that 1000 bytes. So what I do, I create another area and put those 1000 bytes there and use another segment register to point to it. So if I want to access that data which is got out of this malloc, then I use that particular segment. This is one reason why I need multiple data segments, correct, because there is a necessity for us to do dynamic memory allocation, and when I do dynamic memory allocation I need lot more data which I may not get it in consecutive location. Else what I should do, to get it in consecutive location I should push data away and create space. So every time I execute a malloc, can I do a garbage collection? I cannot do a garbage collection, because its garbage collection is really time consuming. Sometimes you boot your system, it takes lot of time for it to basically execute, right. Suddenly it becomes slow. What it does lot of garbage collection. That is why even in normal big services like your financial services, they advise at regular intervals shut down your server and then reboot it. Why? Because sometimes suddenly what happens in the mid of the day when real business is happening, suppose your 640 gigabyte server starts garbage collection, right, you are gone, okay, it will kill your performance. So that is why they say at regular occasions please do garbage collection and keep your garbage away, right. So that is one of the reason why I am giving this as a case study here, because I give this, I believe that we should discuss about this here, because we need to have a clear mapping of why certain things are there in the architecture. That is one big difference in the education that we see everywhere now. Lot of things, how it is done, what is done and how it is done is very, very clearly explained, but why it is done is not basically explained. And you as teachers or students or industry, I think it is very, very important that you understand why certain things are there, right. Please keep asking why, right, and that will give you a lot more answers. And for information security, it is why that is going to solve the problem. You should question everything that comes there and try to get a convincing answer for that, okay, right. So
Sir,
ah
under the Vidya,
yeah,
can you also say that if we have a single index and if you want to access from two different arrays, like in the case of string copy or something, we may need multiple segments?
exactly. So exactly. So if I am for example, if you go to the Intel developer manual, which I want you to go and start looking at this evening and probably have it as a bedtime story today for all the attendees, there are instructions called move SB, move SD, move SW, move string bytes, move string word, move string double word, okay. All these move strings are basically to copy, they are basically intended to do mass copying from one set of memory locations to another, and they had been introduced, in my opinion, I do not know, we have to ask the instruction set architect of Intel to get an idea of that, but I think Intel came out with that first. I think it was done with a view to do process migration specifically from a point of either memory banking and performance issues. When I go from one process to another and I have a non-uniform memory architecture, things like that would have been very useful, and garbage collection from a operating system point of view. So there, when you look at that instruction, there is a source and there is a destination block. The source block is given by one segment register and a counter. It says in this block from this address, which is another register, and this many bytes, that is a counter, move it to this segment, this block pointed to by this segment register, and within that segment this address offset, okay. So there are there are 2 segment registers, 2 offset registers within that segment and 1 counter involved in each of this instruction implied. So, that move SB is just 1 byte, but then there are 5 registers used, 2 segment registers, 3 general purpose registers, 2 for telling the offset and 1 for giving the byte. Okay. So, what Vidya told is correct, that we will also use this multiple segments to move chunks of data from one part to another part, and specifically this is needed in the case of process migration and problems like garbage collection that we saw here, right. Yes. Okay, good. So, before we wind up the session, the next important thing that segmentation will teach us is this multi-process context switching. Please understand, this is very, very important. So, we have all the servers today that are working are multi-user operating system. Even our mobile phone has multi-processes running there. So, it is not just user, even a single user can spawn multiple processes. So, this is a multi-process operating system. So, that means several processes will be coexisting in the same RAM memory, okay, at the same point of time. Now, what will happen is that, please note, this is the memory that we have shown here. There is CS, there are 2 processes, process 1, process 2, and each process has a code segment, a data segment and a stack segment. So, you see 6 segments here, process 1 CS, process 1 DS, process 1 SS, process 2 CS, process 2 DS and process 2 SS. They need not be consecutive, the segments need not be consecutive, but internally each segment should be contiguous, right. It is not necessary that CS, DS and SS all should be in contiguous locations, but CS individually should be contiguous, DS individually should be contiguous, etc. Now, when process 1 is executing, the CS, DS and SS will point to that. When process 2 is executing, it will now point to that string. So, what I mean by switching from process 1 to process 2 is to just go and change the value of that segment register, and immediately my context switch happens. So, I need not do anything else. So, these are all some of the important things that come out of this segmentation. So, we have already seen that there is an ease of compilation, there is a process movement, process mobility is ensured. Then in the previous slide we saw that we could have multiple segments, and we also motivated several things for that, and then now we could have what we call as this multi-process context switching. In addition to this, the x86 architecture basically has control registers. There are 3 control registers that are of importance as of now, where each of these control registers are 32-bit in length. The CR0 is very important. The CR0 has some very, very interesting bits. The bit 0 is 1 which will make the processor to protected mode. The bit 3 is 1 which will indicate whether there is a task switching that is happening. The bit 31 is 1 where you enable paging, okay. So, there are 3 bits, please remember these bits that we will be using them extensively down the line. Bit 0 is the protected mode enable bit, bit 3 is a task switch, you will understand whether a task switch has happened or not, and bit 31 is a bit which will enable virtual memory in your stuff. The CR2 is a read only register from the user's perspective, it will give you which was the last address which created a page fault, and the CR3 page fault is for paging for virtual memory, and the CR3 will store the page directory address for the paging, okay. So, just remember that CR2 will give you address for page fault, CR3 will store the base address for directory, and as we go on to paging etc., we will be using these control registers, right. In addition, there are several registers, basically DR0, DR1, DR2, DR3, DR6, DR7. Then DR0 to DR3 can hold 4 linear addresses, breakpoints. So, you do the GDB, right, you say break at this, so where we want to break I can put those addresses here, and when you reach those addresses automatically the architecture will do a break and it will transfer it to as interrupt service routine in which will serve that break, right. When you break, then you go and query what is the variable address, etc., variable value, etc. Then there is a DR6 which is a debug status register indicating the circumstances that may have caused the last debug fault, okay. And DR7 is a debug control register. By filling in the various fields of this register you can control the operation of the 4 linear address breakpoints, okay. So a lot of things can be done here. So these are registers. So why are these? The control registers are very important to realize certain functionalities, to enable and disable certain functionalities. The debug registers gives you much more insight into the working of the program. So later part, when we want to develop certain utilities that will go and monitor a program, I think these are the registers, at least a debug register are ones which can be extensively used. So down the course, not only this course but the subsequent courses, we may try and use these debug registers, okay. So with this we end this session.
Yeah, I was asking about, I mean, you asked us a question on why we should have multiple segment registers.
Okay.
I was just saying,
yeah.
we
Right. So, now I remember. So, so the thing is that if I want a very huge segment, right, for example, if I take a 32-bit architecture, I need a segment which is as large as 4 gigabyte. Now, if you look at the segment size, right, it is the segment, there is something called a segment descriptor. As we go down we will see that the segment descriptor is only 20 bits in size. If I say it is 20 bits, that means I can, what is 20 bits? 1 MB, right. But then Intel, because it is a complex instruction set, right, it has to prove its complexity every time, okay. It has one bit called a granularity bit in the segment descriptor. If I set that bit to 1, then every integer that I store should be multiplied by 4 KB, right. 4 KB is 12 bits. So if I that bit is 0 and I put limit as 10, it is then 10 bytes. If I make that bit 1 and store 10 here, it is 10 into 4 KB, that is 40 KB, right. So if I make that bit 1 and I store all the 20 bits, that means it is 2 power 20 into 12, 2 power 12, it is 4 GB. So I could have a segment which is as large as 4 GB or as small as 1 MB, meaning in terms of limits, okay. Now this is how Intel has addressed large segment versus small segment, but this is sort of very binary because 1 MB to 4 GB is too huge a space. If I say it is 4 GB, then what happens? Essentially the entire address space is available to me. If I say 1 MB, it is very restrictive. Why I am answering Vidya's question in this big way is that you understand this has become a very big problem. If you look at some of the OS, right, none of the OS actually uses segmentation for protection. The OS where we have seen the source code available, if you carefully look at the source code, the operating system does not use segmentation for protection. The operating system uses paging for protection, right. Why it does not use segmentation for protection is, since it does not use segmentation for protection, it just creates one 4 GB memory, one 4 GB segment and say it is open to all, okay, right. So anybody can do anything because it is one least privilege level, one 4 GB is given. The reason I also thought, why is this reason? Because it has either segments of size 1 MB or it has segments of size 4 GB, and this is too restrictive for because today a program can have segments which are more than 1 MB in size, correct, right, executables more than 1, and maybe this is the reason why Intel type of this set of feature is not being used in practice, okay. So One reason, yeah, this could also be a reason, Vidya. Well, I want a 2 MB memory segment, I can't afford to create a 4 GB for that. So, I will use 2 segment registers to create 1 MB plus 1 MB rather than one 4 GB segment. So, that could also be a valid reason, and this is also a reason why segmentation is not being used prevalently for protection. But segmentation essentially has so much good things, and we can get lot of process isolation done through segmentation. But because of this particular reason, probably because of this particular reason, the second reason would be portability. Each architecture has its own whims and fancies about segmentation. So, I can't have a compiler compile for the segmentation. See, I need to have an operating system. So, I make a Linux, I can't make Linux for Intel, Linux for this. So, I want one Linux which is portable. So, people did not try and do things for each architecture specific things, and that is also precisely some of the reason why the operating systems do not use these hardware infrastructure that is available, and that it does not use these hardware infrastructure positively, and that is precisely some of the reasons why you miss some of the security features that are made available. Okay. So, this is sort of an elaborate answer. That is a wonderful question, and I think this answer is throws lot of light on architectural aid to security.